Object-oriented programming, or OOP, is a programming paradigm that organizes code around objects rather than functions and logic. Think of objects as digital representations of real-world things, like a car, a user account, or a shopping cart. Each object contains both data, called attributes, and behaviors, called methods. This approach mirrors how we naturally think about the world, making code more intuitive and manageable. OOP revolutionized software development by solving critical problems that plagued earlier programming approaches. It makes large code bases maintainable by organizing code into self-contained, reusable units. When building complex applications, from mobile apps to enterprise systems, OOP provides a clear structure that teams can understand and collaborate on effectively. It reduces code duplication, makes debugging easier, and allows developers to model real-world problems naturally in their code. The journey began in the 1960s with Simula, a language designed for simulation programs in Norway. Simula introduced the concept of classes and objects for the first time. In the 1970s, Alan Kay and his team at Xerox PARC developed Smalltalk, which fully embraced object-oriented principles and coined the term object-oriented programming. The 1980s saw OOP go mainstream with C++, which added object-oriented features to the popular C language. By the 1990s, languages like Java and Python emerged, making OOP accessible to millions of developers worldwide. Before OOP, procedural programming dominated. In procedural programming, you write sequences of instructions that manipulate data. While simple for small programs, this approach becomes chaotic as projects grow. OOP offers better organization, code reuse through inheritance, and easier maintenance. Today, OOP remains one of the most influential programming paradigms, powering everything from web applications to video games, and forming the foundation that modern developers build upon. Now that we understand what OOP is and where it came from, let's dive into its most fundamental concepts, classes and objects. These two concepts form the absolute foundation of object-oriented programming, and understanding them is essential to everything else we'll cover in this video. Imagine you're an architect designing houses. Before builders can construct a house, you create detailed blueprints that specify every aspect. How many rooms, where the doors go, the plumbing layout, electrical wiring, and so on. These blueprints aren't the house itself. They're a plan, a template that describes what the house should look like and how it should function. In object-oriented programming, a class serves exactly this purpose. A class is a blueprint or template that defines the structure and behavior of objects. It specifies what data an object will hold and what actions it can perform. Just like you can use the same house blueprint to build multiple houses, you can use the same class to create multiple objects. Let's think about a real example. Suppose we want to model a car in our program. We would create a car class that defines what every car should have. Every car has properties like color, brand, model, year, and current speed. Every car also has behaviors like starting the engine, accelerating, braking, and turning. The class definition captures all of these characteristics in code. The class itself doesn't represent any specific car. It's just a blueprint. It tells us that any car we create will have these properties and these behaviors, but it doesn't give us an actual car we can drive. That's where objects come in. An object is a concrete instance of a class. If the class is the blueprint, the object is the actual house built from that blueprint. When we create an object from a class, we call this process instantiation. We're creating an instance of that class. Going back to our car example, we might create several objects from our car class. We could create a red Toyota Camry from 2020, a blue Ford Mustang from 2019, and a black Tesla Model 3 from 2023. Each of these is a separate object, a unique instance of the car class. They all share the same structure defined by the class, but each has its own specific data. This is one of the most powerful aspects of OOP. We write the class definition once, and then we can create as many objects as we need. Each object is independent. Changing the color of one car object doesn't affect the others. Starting the engine of one car doesn't start all the cars. Each object maintains its own state. Let's talk about attributes in more detail. Attributes, also called properties or fields, are the data that objects hold. They represent the state of an object at any given moment. In our car class, attributes might include the color, brand, model, year, current speed, fuel level, and whether the engine is running. When we create a new car object, we typically initialize these attributes with specific values. One car might have color set to red, brand set to Toyota, and current speed set to 0. Another car object might have completely different values. These attributes define what the object is at any point in time. Attributes can be of any data type. Some might be simple values like numbers or text strings. Others might be more complex, like lists or even other objects. A car might have an engine attribute that is itself an object with its own properties like horsepower and number of cylinders. This ability to nest objects inside other objects allows us to model complex real-world relationships. Now let's discuss methods. Methods are functions that belong to a class. They define what objects of that class can do. Methods represent the behaviors or actions that objects can perform. They're the verbs to the attributes nouns. In our car class, we might have a method called startEngine. When we call this method on a car object, it changes the engine running attribute to true. We might have an accelerate method that increases the current speed attribute. A brake method would decrease the speed. A turn method might change the direction the car is facing. Methods can access and modify the object's attributes. That's what makes them powerful. The accelerate method needs to know the current speed, so it can increase it. The startEngine method needs to check if the engine is already running. Methods work with the data stored in the object's attributes to produce meaningful behaviors. Methods can also take parameters, which are inputs that modify how the method behaves. Our accelerate method might take a parameter specifying how much to increase the speed. If we call accelerate with a value of 10, the car speeds up by 10 units. If we call it with 20, it speeds up by 20 units. Methods can also return values. We might have a get fuel level method that returns the current fuel level, so we can display it to the user. A calculate trip distance method might perform some calculations and return the result. One special type of method is the constructor. The constructor is a method that runs automatically when we create a new object. It initializes the object's attributes with starting values. When we create a new car object, the constructor might set the current speed to 0, the engine running to false, and the fuel level to full. It might also take parameters, so we can specify the color, brand, and model when we create the car. The relationship between classes and objects is sometimes called the class-instance relationship. The class defines the type, and objects are instances of that type. Think of it like the relationship between a species and individual animals. Dog is a species, a classification. Fido, Rex, and Buddy are individual dogs, instances of the dog species. Each has the characteristics of a dog, but each is a unique individual. Let's consider another practical example to solidify these concepts. Imagine we're building a social media application. We would need a user class. This class would define what every user in our system has and can do. The user class might have attributes like username, email, password, date of birth, profile picture, list of friends, and list of posts. These attributes hold the data that makes each user unique. The user class would also have methods. There might be a create post method that adds a new post to the user's list of posts, an add friend method that adds another user to the friend list, a change profile picture method that updates the profile picture attribute, a calculate age method that uses the date of birth to determine how old the user is. When someone signs up for our social media platform, we create a new user object. We instantiate the user class with that person's specific information. If John signs up, we create a user object with username John, his email, his password, and so on. If Sarah signs up, we create another user object with her information. Both are instances of the user class, but they're completely separate objects with their own data. This separation is crucial. When John creates a post, it's added to his user object's list of posts, not Sarah's. When Sarah adds a friend, it updates her friend list, not John's. Each object maintains its own independent state. Classes can also have class-level attributes and methods, sometimes called static attributes and methods. These belong to the class itself rather than to individual objects. For example, our user class might have a class-level attribute that counts the total number of users. Every time we create a new user object, we increment this counter. It's not specific to any one user. It's information about all users collectively. Similarly, a class-level method might be something like validate email format. This method checks if an email address is valid, but it doesn't need to work with any specific user's data. It's a utility function that belongs to the user class conceptually, but doesn't require an actual user object to work. The power of classes and objects becomes even more apparent when we consider how they promote code organization and reusability. Instead of having scattered variables and functions throughout our code, everything related to cars is bundled together in the car class. Everything related to users is in the user class. This makes our code much easier to understand and maintain. If we need to add a new feature to cars, we know exactly where to go. The car class. If there's a bug in how users add friends, we look at the add friend method in the user class. This organizational clarity is invaluable in large projects with thousands or millions of lines of code. Classes also enable code reuse. Once we've written and tested our car class, we can use it throughout our entire application. We can even use it in other projects. We don't have to rewrite the logic for how cars work every time we need a car in our program. We just create a new instance of the car class. Let's think about a video game as another example. A game might have many different types of entities, players, enemies, items, obstacles, and so on. Each of these would be represented by a class. An enemy class might have attributes like health points, attack power, defense, position on the game map, and current state like idle, patrolling, or attacking. It would have methods like take damage, attack player, move toward target, and drop loot. When the game starts, we don't just have one enemy. We create multiple enemy objects, each representing a different enemy in the game world. One goblin here, 2 orcs there, a dragon in the cave. Each is an instance of the enemy class, but each has its own health, position, and state. When the player attacks one enemy, only that enemy's health decreases. The others are unaffected. This object-based approach makes game development much more manageable. Imagine trying to track dozens or hundreds of enemies without objects. You'd need separate variables for each enemy's health, position, and state. The code would become impossibly complex. With objects, each enemy is a self-contained unit that knows its own state and can manage its own behavior. Another key aspect of objects is encapsulation, which we'll cover in more depth later, but it's worth mentioning now. Objects encapsulate, or bundle together, data and the methods that work on that data. This keeps related things together and prevents outside code from messing with an object's internal state in unexpected ways. For instance, we don't want code outside the car class to directly set the current speed to a negative number. That doesn't make sense. Instead, we provide methods like accelerate and brake that change the speed in controlled, predictable ways. The object's internal data is protected, and we interact with it through well-defined methods. To wrap up this section, remember these key points. A class is a blueprint or template that defines the structure and behavior of objects. An object is a concrete instance of a class with its own specific data. Attributes are the data that objects hold, representing their state. Methods are the functions that objects can perform, representing their behaviors. The constructor is a special method that initializes new objects. Classes provide organization, grouping related data and behaviors together. Objects provide modularity, allowing us to create multiple independent instances from the same class. Together, classes and objects form the foundation of object-oriented programming, enabling us to model complex systems in a natural, manageable way. In the next section, we'll explore encapsulation in detail, learning how to protect object data and control access to it. But for now, make sure you understand classes and objects thoroughly. They're the building blocks upon which everything else in OOP is built. Now that we understand classes and objects, let's explore one of the most important principles in object-oriented programming: encapsulation. Encapsulation is often described as bundling data and methods together, but it's much more than that. It's about controlling access to that data and hiding the internal details of how an object works. Think of encapsulation like a car's dashboard. When you drive a car, you interact with simple controls: a steering wheel, pedals, and a gear shift. You don't need to understand how the engine combusts fuel, how the transmission shifts gears, or how the braking system distributes pressure to each wheel. All that complexity is hidden under the hood. The dashboard provides a simple, safe interface to a complex machine. This is exactly what encapsulation does in programming. It hides the complex internal workings of an object and exposes only what's necessary through a clean, simple interface. This principle is sometimes called information hiding, and it's fundamental to writing maintainable, robust code. Let's start with the concept of data hiding. In the previous section, we talked about attributes that store an object's state. Without encapsulation, anyone could access and modify these attributes directly from outside the object. This creates serious problems. Imagine our car class has a speed attribute. If external code can directly set this attribute, someone might accidentally or intentionally set the speed to a negative number, or to an impossibly high value like 10,000 miles per hour. They might set it to a text value instead of a number, breaking the entire program. Without protection, the object's data can become inconsistent or invalid. Encapsulation solves this by making attributes private. A private attribute can only be accessed from within the class itself. Code outside the class cannot see or modify it directly. This protects the object's internal state from unauthorized or incorrect modifications. But if attributes are private, how do we work with them? This is where access modifiers come in. Access modifiers are keywords that control the visibility of attributes and methods. The three main access levels are public, private, and protected. Public means the attribute or method is accessible from anywhere. Any code, inside or outside the class, can use it. This is appropriate for methods that form the object's interface, the operations we want users of the class to perform. Private means the attribute or method is only accessible within the class itself. No external code can touch it. This is appropriate for internal implementation details that shouldn't be exposed. Protected is a middle ground. It means the attribute or method is accessible within the class, and also in any classes that inherit from it. We'll talk more about inheritance later, but for now, understand that protected is more restrictive than public, but less restrictive than private. Different programming languages implement these access modifiers differently. Some languages like Java use keywords, public, private, and protected. Python uses naming conventions. A single underscore prefix suggests an attribute is internal, and a double underscore makes it more private. Other languages have their own approaches, but the concept remains the same: controlling who can access what. Let's return to our car class example. We would typically make the speed, fuel level, and engine running attributes private. This prevents external code from setting invalid values. But we still need ways to read and modify these values in controlled ways. This is where getters and setters come in. A getter is a public method that returns the value of a private attribute. A setter is a public method that modifies the value of a private attribute, usually with validation to ensure the new value is valid. For our car class, we might have a getSpeed method that simply returns the current speed. This allows external code to read the speed without giving them direct access to modify it. We might have a setSpeed method, but instead of allowing any value, it checks that the speed is non-negative and within a reasonable range before updating the attribute. Actually, we probably wouldn't even have a setSpeed method. Instead, we'd have methods like accelerate and brake that change the speed in controlled, realistic ways. The accelerate method might increase the speed, but only up to the car's maximum speed. It might also check that the engine is running before allowing acceleration. The brake method decreases the speed, but never lets it go below zero. This is the power of encapsulation. By hiding the speed attribute and providing controlled methods to interact with it, we ensure the car's speed is always valid and changes only in ways that make sense. The object maintains its own integrity. Let's consider a more detailed example with a bank account. A bank account class might have a balance attribute that stores how much money is in the account. This should definitely be private. We don't want external code randomly changing someone's account balance. Instead, we provide public methods like deposit and withdraw. The deposit method takes an amount, validates that it's positive, and adds it to the balance. The withdraw method checks that the requested amount doesn't exceed the balance, ensures the amount is positive, and then subtracts it from the balance. These methods enforce business rules. You can't deposit negative money. You can't withdraw more than you have, unless we implement an overdraft feature. By controlling access through methods, we guarantee that the account balance is always accurate and changes only through legitimate transactions. The get balance method might be public, allowing account holders to check their balance, or it might be protected or private, depending on our design. Maybe we only want the balance accessible through a formatted statement method that shows the balance along with other account information. Encapsulation also allows us to change the internal implementation without affecting external code. Suppose our bank account class initially stores the balance as a simple number. Later, we decide to store it as an integer representing cents instead of a decimal representing dollars. This gives us more precision and avoids floating point arithmetic issues. If external code accessed the balance directly, this change would break everything. Every piece of code that reads or writes the balance would need to be updated. But with encapsulation, the change is confined to the bank account class. The deposit and withdraw methods handle the conversion between dollars and cents internally. The get balance method returns the value in dollars, converting from cents. External code doesn't know and doesn't care how the balance is stored internally. This is what we mean when we say encapsulation promotes maintainability. It creates a clear separation between the public interface and the private implementation. We can change the implementation as long as we maintain the interface. This flexibility is invaluable in large, evolving code bases. Encapsulation also improves debugging. When something goes wrong with an object state, we know exactly where to look. The methods within that class. If a bank account somehow has a negative balance when it shouldn't, we examine the deposit and withdraw methods. We don't have to search through the entire code base, wondering where some random piece of code might have modified the balance. Let's think about another example. A user class for our social media application. The user's password should absolutely be private. We never want external code to read or modify the password directly. Instead, we provide a set password method that hashes the password before storing it, and a check password method that takes a password attempt, hashes it, and compares it to the stored hash. The actual password hash is never exposed. The user's email might have a getter that returns the email, but the setter validates that the provided string is actually a valid email format before updating the attribute. The username might be read-only after the account is created, so we have a getter but no setter at all. The user's friends list might be private, and we provide methods like add friend, remove friend, and get friends. The get friends method might return a copy of the friends list rather than the actual list itself. This prevents external code from modifying the list directly, bypassing any logic we have in add friend and remove friend. This concept of returning copies rather than direct references is another aspect of encapsulation. If we return the actual friends list object, the caller could add or remove items from it, circumventing our methods. By returning a copy, we maintain control over how the friends list changes. Encapsulation isn't about being secretive or making things difficult. It's about creating clear contracts. The public methods of a class form a contract. These are the operations you can perform, and if you use them correctly, the object will behave correctly. The private internals are implementation details that might change, and users of the class shouldn't depend on them. This contract-based thinking leads to better design. When creating a class, we think carefully about what operations should be public. What does someone using this class actually need to do? Everything else can and should be private. This keeps our public interface clean and minimal, making the class easier to understand and use. Good encapsulation also follows the principle of least privilege. Give each piece of code the minimum level of access it needs to do its job. If a method only needs to read an attribute, don't give it the ability to modify it. If external code doesn't need to access an attribute at all, make it private. Some languages and paradigms take encapsulation even further. In some object-oriented languages, you can have multiple levels of privacy within a single class. You might have private methods that are only used by other methods within the class. These helper methods break down complex operations into smaller steps, but aren't meant to be called from outside. Let's consider a more complex scenario. Suppose our car class has a method called perform maintenance. This method needs to do several things. Check the oil level, check the tire pressure, test the brakes, and so on. We might implement this as a public perform maintenance method that calls several private helper methods. Check oil, check tires, test brakes. The helper methods are implementation details. Users of the car class don't need to know or care about them. They just call perform maintenance, and it handles everything. This hierarchical organization is another benefit of encapsulation. We can have public methods that provide high-level functionality, built on private methods that handle low-level details. The public interface remains simple, while the internal implementation can be as complex as necessary. Encapsulation also plays a crucial role in team development. When multiple developers work on a project, encapsulation creates boundaries. One developer can work on the internal implementation of a class, while another developer uses that class through its public interface. As long as the interface remains stable, they can work independently. Imagine a team building a game. One developer is responsible for the physics engine class that handles collision detection and movement. Another developer is creating the enemy AI class that controls how enemies behave. The AI developer doesn't need to understand how collision detection works internally. They just need to know the public methods. Check collision, move object, apply force, and so on. The physics developer can optimize and improve the collision detection algorithms without affecting the AI code. Without encapsulation, these developers would be constantly interfering with each other's work. The AI code might depend on specific internal details of the physics engine. When the physics developer changes those details, the AI code breaks. With encapsulation, there's a clear boundary. The physics engine's public interface is the contract between the two systems. Now, encapsulation isn't always perfect or easy. One challenge is finding the right balance between encapsulation and convenience. Sometimes, being too strict with encapsulation makes the code cumbersome. We might end up writing dozens of simple getter and setter methods that don't add much value. Some modern languages and frameworks provide shortcuts. Properties, for example, allow you to write what looks like direct attribute access, but actually calls getter and setter methods behind the scenes. This gives you the convenience of simple syntax with the protection of controlled access. Another consideration is that encapsulation can sometimes hide too much. If debugging requires understanding what's happening inside an object, excessive encapsulation can make that difficult. Good design balances encapsulation with observability. We might provide read-only access to certain internal state for debugging purposes, or logging methods that expose what's happening internally. To summarize this section, encapsulation is the principle of bundling data with the methods that operate on that data and restricting direct access to an object's internal state. We use access modifiers like public, private, and protected to control visibility. We use getters and setters to provide controlled access to private attributes. We design classes with clear public interfaces that hide implementation details. Encapsulation protects object integrity by preventing invalid states. It improves maintainability by allowing internal changes without affecting external code. It aids debugging by localizing where state changes can occur. It enables team collaboration by creating clear boundaries between components. In the next section, we'll explore inheritance, which allows us to create new classes based on existing ones, reusing and extending their functionality. But the encapsulation we've learned here will continue to be important, as we'll see how access modifiers interact with inheritance. Make sure you understand encapsulation well before moving forward, as it's a cornerstone of object-oriented design. Welcome to one of the most powerful concepts in object-oriented programming, inheritance. Inheritance allows us to create new classes based on existing ones, inheriting their attributes and methods while adding new functionality or modifying existing behavior. This principle enables massive code reuse and helps us model hierarchical relationships that exist in the real world. Let's start with a fundamental analogy. Think about biological inheritance. You inherit traits from your parents: eye color, height, blood type, and many other characteristics. But you're not an exact copy of your parents. You have your own unique traits too. You might have your mother's eyes, but your father's nose. You might develop skills and characteristics that neither parent has. Inheritance in programming works similarly. We create a parent class, also called a base class or superclass, that defines common attributes and methods. Then we create child classes, also called derived classes or subclasses, that inherit everything from the parent, but can add their own unique features or modify inherited ones. Why is this useful? Imagine you're building a zoo management system. You need classes for different animals: lions, elephants, penguins, snakes, and dozens of others. Each animal has unique characteristics, but they also share many common features. All animals have a name, age, and species. All animals eat, sleep, and make sounds, though the specifics vary. Without inheritance, you'd have to write the name, age, and species attributes in every single animal class. You duplicate the eat, sleep, and make sound methods across all classes. This creates enormous amounts of redundant code. When you need to change something common to all animals, you'd have to modify it in dozens of places. It's inefficient, error-prone, and difficult to maintain. With inheritance, we create a single animal class that contains all the common attributes and methods. Then we create specific classes like lion, elephant, and penguin that inherit from animal. Each inherits the common features automatically while adding or customizing features specific to that animal type. Write once, use everywhere. Let's build this example step by step. Our animal class might have attributes like name, age, species, and hunger level. It might have methods like eat, sleep, and make sound. This class captures everything common to all animals. Now we create a lion class that inherits from animal. In most programming languages, we specify this inheritance relationship when defining the class. The syntax varies by language, but the concept is the same. Lion is a child of animal, or lion extends animal, or lion inherits from animal. The moment we establish this relationship, the lion class automatically has all the attributes and methods from animal. We don't have to rewrite them. A lion object has a name, age, species, and hunger level. It can eat, sleep, and make sound. We get all of this for free through inheritance. But lion can also have its own unique attributes. Maybe lion has a pride name attribute, representing which pride the lion belongs to. Maybe it has a main color attribute that's specific to lions. These attributes exist only in the lion class, not in the general animal class. Similarly, lion can have its own unique methods. Maybe it has a roar method that's specific to lions. Maybe it has a hunt and pack method. These are lion-specific behaviors that don't apply to all animals. This is the essence of inheritance. Reuse common code from the parent while extending with child-specific features. The relationship is often described as an is a relationship. A lion is an animal. An elephant is an animal. This is a test helps us know when inheritance is appropriate. Now let's talk about method overriding, one of the most important aspects of inheritance. Sometimes a child class needs to do something differently than the parent class. The parent class might have a method, but the child needs a specialized version of that method. Going back to our animal example, the animal class might have a make sound method, but the specific sound varies by animal. Lions roar, elephants trumpet, penguins squawk. Each animal makes a different sound. Method overriding allows the child class to provide its own implementation of a method that already exists in the parent class. The lion class overrides make sound to produce a roar. The elephant class overrides it to produce a trumpet sound. The penguin class overrides it to produce a squawk. When we call make sound on a lion object, it executes the lion version, not the generic animal version. The child's implementation replaces the parent's implementation. This is method overriding in action. But here's something important. The overridden method in the child can still access the parent's version if needed. Many languages provide a way to call the parent's method from within the child's overridden method. This is often done with a keyword like super or base. Why would we want this? Sometimes the child wants to extend the parent's behavior rather than completely replace it. For example, the animal class's eat method might decrease the hunger level attribute. The lion class might override eat to do everything the animal version does, plus additionally increase its energy level for hunting. The lion's eat method calls the parent's eat method using super, then does its additional logic. This ability to call parent methods gives us flexibility. We can completely replace a parent's method, or we can extend it by calling the parent version and adding more functionality. Let's explore a different example to see inheritance in action. Imagine we're building a shape drawing application. We need different shapes: circles, rectangles, triangles, and so on. Each shape has common features, but also unique characteristics. We create a shape class as our parent. Every shape has attributes like X position, Y position, and color. Every shape needs methods like draw, move, and calculate area. The shape class defines these common elements. Now we create child classes. A circle class inherits from shape. It adds a radius attribute specific to circles. It overrides the calculate area method to compute the area using the circle formula, pi times radius squared. It overrides the draw method to draw a circle on the screen. A rectangle class also inherits from shape. It adds width and height attributes. It overrides calculate area to compute width times height. It overrides draw to render a rectangle. Each shape shares the common infrastructure from shape, but implements its own specific behavior. If we want to add a new shape, we create a new class that inherits from shape, add any unique attributes, and override the necessary methods. The common functionality comes for free. Inheritance creates hierarchies. A child class can itself be a parent to other classes. We might have an animal parent class with a mammal child class and a bird child class. Then mammal might be the parent of lion, elephant, and dolphin. Bird might be the parent of penguin, eagle, and parrot. This creates a tree-like hierarchy. Each class in this hierarchy inherits from all its ancestors. A lion inherits from mammal, and mammal inherits from animal, so lion inherits from both. A lion has all the attributes and methods from animal, plus everything from mammal, plus its own lion-specific features. This multi-level inheritance allows us to organize code in increasingly specific categories. Animal has features common to all animals. Mammal adds features specific to mammals, like giving live birth and producing milk. Lion adds features specific to lions. Each level adds specificity without duplicating the more general features. Now let's discuss different types of inheritance. The examples we've discussed so far are single inheritance, where each child class has exactly one parent. Some programming languages support multiple inheritance, where a child class can inherit from multiple parents simultaneously. Multiple inheritance is powerful but complex. Imagine a flying fish. It's both a fish and something that flies. Should it inherit from fish or from flying animal? With multiple inheritance, it could inherit from both, gaining features from each. However, multiple inheritance creates complications. What if both parents have a method with the same name? Which one does the child inherit? This is called the diamond problem, and different languages handle it differently. Some languages don't support multiple inheritance at all to avoid these issues. Others support it, but require careful management. Many languages that don't support multiple inheritance offer alternatives like interfaces or mixins, which we'll touch on later. These provide some benefits of multiple inheritance without the complexity. Let's talk about the protected access modifier we mentioned earlier. Protected attributes and methods are accessible within the class and within any child classes. This is the middle ground between public and private. When designing a parent class, we use protected for things that child classes might need to access or modify, but that shouldn't be public. In our animal class, we might have a protected attribute for metabolism rate. Child classes might need to access this when implementing their specific eat methods, but external code shouldn't modify it directly. Protected access gives child classes more flexibility while still maintaining encapsulation from the outside world. It's part of the contract between parent and child classes. Inheritance also interacts with constructors in interesting ways. When we create an object of a child class, the parent class's constructor runs first, then the child class's constructor. This makes sense. We need to initialize the parent's attributes before we can initialize the child's additional attributes. In our lion class, When we create a new lion object, the animal constructor runs first to initialize the name, age, and species. Then the lion constructor runs to initialize the pride name and main color. The child constructor typically calls the parent constructor explicitly, passing the necessary values. This chaining of constructors ensures that objects are properly initialized at every level of the inheritance hierarchy. It's automatic in some languages and explicit in others, but the principle is the same. Now let's discuss when to use inheritance and when not to. Inheritance is appropriate when there's a clear is a relationship. A lion is an animal. A circle is a shape. These are natural hierarchies that map to real-world relationships. Inheritance is not appropriate for has a relationships. A car has an engine, but cars shouldn't inherit from engine. That would be nonsensical. Instead, the car class should have an engine attribute that is an engine object. This is called composition, and it's often more appropriate than inheritance. Choosing between inheritance and composition is a key design decision. A good rule of thumb: use inheritance for is a relationships and composition for has a relationships. A student is a person, so student might inherit from person. But a student has a transcript. Student shouldn't inherit from transcript. Overusing inheritance can lead to problems. Deep inheritance hierarchies become difficult to understand and maintain. If you have to trace through 5 or 6 parent classes to understand how something works, the design is probably too complex. Favor shallow hierarchies when possible. Another issue with inheritance is that it creates tight coupling between parent and child. Changes to the parent class can break child classes. If you modify a method in the parent, all children that override that method or depend on it might be affected. This fragility is sometimes called the fragile base class problem. Despite these cautions, inheritance remains incredibly useful when applied appropriately. It's one of the main mechanisms for code reuse in object-oriented programming. It allows us to build complex systems from simpler components, adding specificity at each level. Let's consider one more practical example: a game with different types of characters. We might have a character parent class with attributes like health, position, and inventory. It has methods like take damage, move, and use item. We create child classes for different character types. A player class might add attributes for experience points and skills. An enemy class might add attributes for aggression level and patrol route. An NPC class for non-player characters might add dialogue options and quest information. Each inherits the basic character functionality, but adds role-specific features. The take damage method might be overridden differently for each. Players might trigger a game over screen when health reaches 0. Enemies might drop loot and remove themselves from the game. NPCs might become hostile or flee. This structure makes the game code much more manageable. Common character logic lives in one place. Role-specific logic is separated into appropriate classes. Adding a new character type is straightforward. Inherit from character and implement the specifics. Inheritance also enables polymorphism, which we'll cover in the next section. But understand that inheritance sets the stage for polymorphism by allowing us to treat objects of different child classes as if they were all objects of the parent class. To summarize, inheritance allows us to create new classes based on existing ones, inheriting their attributes and methods. The child class, or subclass, inherits from the parent class, or superclass. Child classes can add new attributes and methods, and can override parent methods to provide specialized behavior. Inheritance creates hierarchies that model real-world relationships and enable code reuse. Method overriding lets child classes customize inherited behavior. Protected access gives child classes access to parent internals while maintaining encapsulation. Constructors chain from parent to child. Inheritance is appropriate for is a relationships, but not for has a relationships. Use inheritance judiciously to avoid deep hierarchies and tight coupling. When used well, inheritance is a powerful tool for organizing code, promoting reuse, and modeling hierarchical relationships in your domain. In the next section, we'll explore polymorphism, which builds directly on the inheritance concepts we've learned here. Polymorphism allows us to write code that works with parent class types, but can handle any child class object, providing tremendous flexibility in how we design systems. Polymorphism is one of the most elegant and powerful concepts in object-oriented programming. The word comes from Greek. Poly means many, and morph means form. Polymorphism literally means many forms. In programming, it refers to the ability of different objects to respond to the same message or method call in different ways. Think about the concept of speaking. When you tell a person to speak, they use their voice. When you tell a parrot to speak, it mimics sounds. When you tell a computer to speak, it uses text-to-speech synthesis. The command is the same, speak, but the implementation varies depending on who or what is doing the speaking. That's polymorphism in the real world. In object-oriented programming, polymorphism allows us to write code that works with objects of a parent class, but that code can actually operate on objects of any child class. We can write general, flexible code that doesn't need to know the specific type of object it's working with. There are two main types of polymorphism: compile-time polymorphism and runtime polymorphism. Let's explore each in detail. Compile-time polymorphism, also called static polymorphism, is resolved during compilation. The compiler determines which method to call based on the method signature. The most common form of compile-time polymorphism is method overloading. Method overloading means having multiple methods with the same name, but different parameters. The methods differ in the number of parameters, the types of parameters, or both. When you call an overloaded method, the compiler looks at the arguments you provide and selects the appropriate version. Let's look at a practical example. Imagine a calculator class with multiple add methods. One version takes 2 integers and returns their sum. Another version takes 3 integers. Another takes 2 decimal numbers. Another takes 2 complex numbers. They all have the same name, add, but different parameter lists. When you call the add method with 2 integers, the compiler selects the 2-integer version. When you call it with 3 integers, it selects the 3-integer version. The method name is the same, but the behavior differs based on the parameters. This is method overloading. Method overloading makes code more intuitive. Instead of having add integers, add decimals, and add complex numbers as separate method names, we have one consistent name. Users of the class don't need to remember multiple names. They just call add with appropriate arguments, and the right version executes automatically. Overloading isn't limited to different parameter counts. You can have methods with the same number of parameters, but different types. A draw method might have one version that takes x and y coordinates as integers, and another that takes them as decimal numbers. Same name, same number of parameters, but different types. The return type alone doesn't distinguish overloaded methods. 2 methods with the same name and parameters, but different return types, would create ambiguity. The compiler wouldn't know which to call. Most languages don't allow this. Constructor overloading is particularly common. A class might have multiple constructors, with different parameter lists. A person class might have a constructor that takes a name only, another that takes a name and age, and another that takes name, age, and address. This flexibility lets users create objects in different ways, depending on what information they have available. Now let's move to runtime polymorphism, also called dynamic polymorphism. This is the more powerful and frequently discussed form of polymorphism. It's resolved during program execution, not compilation. Runtime polymorphism is achieved through method overriding in inheritance hierarchies. Remember from the previous section that child classes can override methods from their parent class. Runtime polymorphism takes this further by allowing us to treat child objects as if they were parent objects, yet still get the child-specific behavior. Let's revisit our animal example. We have an animal parent class with a make-sound method. Lion, elephant, and penguin inherit from animal, and each overrides make-sound to produce their specific sound. Here's where polymorphism becomes powerful. We can write code that works with animal references, but actually operates on lion, elephant, or penguin objects. We can have a list of animal objects that contains a mix of different animal types. We can loop through this list, calling make-sound on each, and each animal produces its appropriate sound. The code doesn't need to know whether it's dealing with a lion or an elephant. It just knows it has an animal, and animals have a make-sound method. At runtime, the program figures out the actual type of each object and calls the correct version of make-sound. A lion produces a roar. An elephant produces a trumpet sound, all from the same generic code. This is incredibly powerful for writing flexible, extensible code. Imagine a zoo simulation. We have a function called feed all animals that takes a list of animals and feeds each one. The function doesn't need separate logic for lions, elephants, and penguins. It just loops through the list, calling the eat method on each animal. Because each animal type overrides eat with its specific behavior, the right thing happens automatically. Lions eat meat, elephants eat vegetation, penguins eat fish. The feed all animals function doesn't care about these details. It works with the animal interface, and polymorphism ensures the correct behavior occurs. This exemplifies the open-closed principle, a key concept in software design. Code should be open for extension but closed for modification. With polymorphism, we can add new animal types without changing the feed all animals function. Create a new snake class that inherits from animal and overrides eat. Now snakes can be fed through the same function without any changes to that function's code. Polymorphism enables us to write code against interfaces rather than concrete implementations. We program to the animal interface, not to specific animal types. This makes code more flexible and maintainable. Let's explore another example, a payment processing system. We have a payment parent class with a process payment method. We create child classes for different payment types: credit card payment, PayPal payment, Bitcoin payment, and so on. Each overrides process payment with the logic specific to that payment method. In our checkout code, we don't need to know what payment method the customer chose. We have a payment object, and we call process payment on it. Whether it's a credit card, PayPal, or Bitcoin, the correct processing logic executes. The checkout code is completely decoupled from the specifics of payment processing. If we want to add a new payment method later, we create a new class that inherits from payment and implements process payment. The checkout code requires no changes. This extensibility is a major benefit of polymorphism. Now let's discuss how polymorphism works under the hood. When you have a parent class reference to a child class object, the reference type and the object type are different. The reference says this is an animal, but the actual object is a lion. This is perfectly legal in object-oriented languages. When you call a method through that reference, the program needs to determine which version of the method to execute, the parent's or the child's. This is called dynamic dispatch or dynamic binding. The program looks at the actual object type at runtime and calls the appropriate method. Most object-oriented languages implement this through a mechanism called a virtual method table or table. Each class has a table listing its methods and where in memory each one is located. When you call a method, the program looks up the method in the objects table and jumps to the correct implementation. This lookup happens at runtime, which is why it's called runtime polymorphism. There's a tiny performance cost compared to calling a method directly, but modern processors are so fast that this cost is negligible in most applications. The benefits of polymorphism far outweigh this minor overhead. Some languages require you to explicitly mark methods as capable of being overridden, using keywords like virtual in C++ or open in Swift. Other languages like Java make methods overridable by default. Python is fully dynamic, so all method calls are effectively polymorphic. Understanding your language's approach to polymorphism is important for using it correctly. But the fundamental concept remains the same across languages. Parent class references can hold child class objects, and method calls resolve to the child's implementation. Let's talk about abstract classes and interfaces, which are deeply connected to polymorphism. An abstract class is a class that cannot be instantiated directly. It exists only to be inherited from. Abstract classes typically contain abstract methods, methods declared but not implemented. Child classes must provide implementations for these abstract methods. Why would we want this? Abstract classes let us define a contract that child classes must fulfill. They enforce a common interface across all children, while allowing each child to implement the details differently. Going back to our shape example, we might make shape an abstract class with an abstract calculate area method. You can't create a generic shape object because it doesn't make sense to calculate the area of an unspecified shape. But every concrete shape, circle, rectangle, triangle, must provide a calculate area implementation. This guarantees that every shape in our system can calculate its area. We can write code that works with shape references, calling calculate area, confident that whatever the actual shape type is, it will have a working implementation. Interfaces take this concept further. An interface is a pure contract with no implementation at all. It lists methods that implementing classes must provide, but it contains no code itself. A class can implement multiple interfaces, gaining the benefits of multiple inheritance without the complications. For example, we might have a drawable interface with a draw method, a movable interface with a move method, and a resizable interface with a resize method. A rectangle class could implement all three interfaces, promising to provide all three methods. A circle might implement drawable and movable, but not resizable. Code can work with these interfaces polymorphically. A function that takes a drawable parameter will accept any object whose class implements drawable, regardless of what that class is or what other interfaces it implements. This is polymorphism through interfaces. Interfaces enable a design technique called dependency injection. Instead of a class creating its own dependencies, they're provided to it through its constructor or methods. The class works with interface types, so any implementation of those interfaces can be injected. This makes code incredibly flexible and testable. In production, you might inject a real database implementation. In testing, you might inject a mock database that doesn't actually access a database but returns predetermined values. The code using the database doesn't know or care which implementation it received, as long as it implements the database interface. Let's consider a logging example. We define a logger interface with methods like loginfo, logwarning, and logerror. We create multiple implementations: file logger writes to files, console logger writes to the console, network logger sends logs to a remote server. Our application code works with the logger interface. We can switch between different logging implementations without changing application code. We can even change which logger we use at runtime based on configuration. This flexibility comes from polymorphism through interfaces. Polymorphism also enables the strategy pattern, a common design pattern. The strategy pattern defines a family of algorithms, encapsulates each in a class, and makes them interchangeable. The client code works with a strategy interface, and different strategies can be swapped in and out. Imagine a sorting application. We might have different sorting algorithms: quick sort, merge sort, bubble sort. We define a sort strategy interface with a sort method. Each algorithm is a class implementing this interface. The application can use any sorting strategy, and we can change strategies dynamically based on the data size or other factors. Without polymorphism, we'd need conditional statements checking which strategy to use and calling the appropriate function. With polymorphism, we just call sort on whatever strategy object we have, and the right algorithm executes. The code is cleaner and more maintainable. Polymorphism also plays a crucial role in frameworks and libraries. A framework might define abstract classes or interfaces that your code extends or implements. The framework calls methods on your code through these abstractions, even though the framework was written before your code existed. For example, a web framework might have a request handler interface with a handle request method. You create classes that implement this interface, and the framework calls handle request when web requests arrive. The framework doesn't know about your specific classes, but through polymorphism, it can work with them. This inversion of control is fundamental to modern software architecture. The framework provides the structure and flow, and your code plugs into it by implementing specified interfaces. Polymorphism makes this possible. Now let's discuss some practical considerations. Polymorphism works best when the parent class or interface represents a meaningful abstraction. Don't create inheritance hierarchies just to use polymorphism. The relationships should reflect real domain concepts. Also, remember that polymorphism requires method overriding, not just inheriting. If child classes don't override any methods, there's no polymorphic behavior. The power comes from different implementations of the same interface. Be cautious about violating the Liskov substitution principle, which states that child class objects should be substitutable for parent class objects without breaking the program. If a child class's override changes behavior so drastically that code expecting a parent object would break, you violated this principle and your polymorphism isn't sound. For instance, if the parent class's method never throws exceptions, but a child's override does, code that doesn't expect exceptions might crash. The child has changed the contract in an incompatible way. Overrides should extend or specialize behavior, not fundamentally alter the contract. Polymorphism can sometimes make code harder to follow because you can't easily see which implementation will execute just by reading the code. Modern development environments help with this by letting you navigate to all implementations of a method, but it's something to be aware of. The flexibility comes with a slight cost in immediate code clarity. Despite these considerations, polymorphism is invaluable. It's what allows object-oriented code to be truly flexible and extensible. It enables us to write code that works with abstractions rather than concrete types, making systems that can grow and adapt without constant rewrites. To summarize, polymorphism means many forms. It allows different objects to respond to the same method call in different ways. Compile-time polymorphism includes method overloading, where multiple methods have the same name but different parameters. Runtime polymorphism comes from method overriding in inheritance hierarchies, where child class objects can be treated as parent class objects but execute child-specific behavior. Abstract classes and interfaces define contracts that concrete classes must implement, enabling polymorphism through shared abstractions. Polymorphism allows code to be open for extension but closed for modification, to work with interfaces rather than implementations, and to be flexible and testable through techniques like dependency injection. In the next section, we'll explore abstraction more deeply, seeing how it relates to all the concepts we've covered and how it helps us manage complexity in large systems. Understanding polymorphism well prepares you for that discussion, as abstraction and polymorphism work hand in hand to create clean, maintainable object-oriented designs. Abstraction is the fourth pillar of object-oriented programming, alongside encapsulation, inheritance, and polymorphism. While these concepts are interconnected, abstraction has a unique role. It's about hiding complexity and showing only what's necessary. Abstraction helps us manage the overwhelming complexity of large software systems by focusing on essential qualities while hiding implementation details. Think about driving a car. When you sit in the driver's seat, you interact with a simplified interface, a steering wheel, pedals, and perhaps a gear shift. You don't see the combustion process in the engine cylinders, the electrical signals controlling the fuel injection, or the hydraulic pressure distribution in the braking system. All that complexity is hidden behind a simple, abstract interface. You think in terms of go, stop, and turn, not in terms of spark plug timing and brake fluid pressure. This is abstraction in action. The car presents an abstract model of transportation. You provide high-level commands, and the complex machinery underneath handles the details. You don't need to understand internal combustion to drive. The complexity is abstracted away. In programming, abstraction works the same way. We create simplified models of complex systems, exposing only what users need to know while hiding intricate implementation details. This makes systems easier to understand, use, and maintain. Abstraction operates at multiple levels. At the most fundamental level, programming languages themselves are abstractions. When you write code in Python or Java, you're working with an abstraction over machine code and hardware operations. You write print hello world, not a sequence of instructions to move bytes into memory addresses and trigger display drivers. The language abstracts away that complexity. Similarly, data structures are abstractions. When you use a list or dictionary, you interact with a high-level interface. Add item, remove item, find item. You typically don't think about how the data structure manages memory internally, how it resizes itself, or how it optimizes lookups. Those implementation details are abstracted away. In object-oriented programming, abstraction means identifying the essential characteristics of an object while ignoring the irrelevant details. It's about creating classes that represent concepts at the right level of detail for your problem domain. Let's explore this with an example. Suppose we're building an e-commerce system. We need to represent products. What are the essential characteristics of a product? It has a name, a price, a description, a stock quantity. It can be purchased, returned, and reviewed. But products have many other details we might ignore. The molecular composition of the materials they're made from, the exact GPS coordinates of where they were manufactured, the first names of the factory workers who assembled them. These details exist in the real world but aren't relevant to our e-commerce system. We abstract them away. Our product class includes only the attributes and methods relevant to e-commerce operations. This is abstraction, choosing what to include and what to exclude based on the context and purpose of our system. Different systems might abstract the same real-world concept differently. A shipping company's system might include product weight and dimensions as essential attributes, which our e-commerce system might not care about. A quality control system might track manufacturing details that both other systems ignore. Each system creates abstractions appropriate to its needs. Abstraction helps us manage complexity by working at the right level of detail. We think in terms of products, customers, and orders, not bits, bytes, and memory addresses. This higher-level thinking is what makes it possible to build large, complex systems. Now let's discuss abstract classes, which we touched on in the polymorphism section. An abstract class is a class that cannot be instantiated on its own. It exists only to be extended by other classes. Abstract classes typically contain abstract methods, methods that are declared but not implemented. Why create a class you can't instantiate? Abstract classes let you define a template that child classes must follow. They establish a contract. If you inherit from this abstract class, you must implement these specific methods. Consider a database system that needs to support multiple database types: SQL databases, NoSQL databases, in-memory caches, and so on. We might create an abstract database connection class with abstract methods like connect, disconnect, execute query, and fetch results. This abstract class doesn't implement these methods because the implementation varies completely between database types. A SQL database connects differently than the NoSQL database. They execute queries using different protocols, but they all need these operations. Concrete classes like MySQL connection, MongoDB connection, and Redis connection inherit from database connection and implement all the abstract methods. Each provides the implementation appropriate for its database type. Our application code can work with database connection references through polymorphism. Functions that need a database connection take a database connection parameter. They don't care whether it's MySQL or MongoDB. They just call the abstract methods, and the correct implementation executes. The abstract class serves as an abstraction layer between the application code and the specific database implementations. The application thinks in terms of generic database operations, not specific database APIs. This is abstraction reducing complexity. Abstract classes can also contain concrete methods, methods with actual implementations. These are common operations that all child classes share. The abstract class might have a concrete log error method that all database connections use, alongside the abstract execute query method that each implements differently. This combination of abstract and concrete methods makes abstract classes powerful. They provide both a contract that children must fulfill and shared functionality that children inherit. Interfaces represent pure abstraction. An interface defines only method signatures, no implementations at all. It's a contract specifying what an implementing class must do, not how to do it. Interfaces are more abstract than abstract classes. An abstract class says here's a partially implemented concept. Fill in the missing pieces. An interface says here's a capability that various unrelated classes might have. Implement it however you want. Let's look at a practical example. We might define a serializable interface with methods like serialize to JSON and deserialize from JSON. Many different classes might implement this interface: product, user, order, shipping address. These classes are completely unrelated in terms of inheritance, but they all need serialization capability. By implementing serializable, each class promises to provide these methods. Code that needs to serialize objects can work with the serializable interface. It doesn't care what the object actually is. If it's serializable, it can be serialized. This is a key aspect of abstraction. focusing on capabilities rather than identity. We don't care what something is. We care what it can do. The interface represents the abstraction of a capability. Multiple interfaces can define different capabilities, and a single class can implement many interfaces. A user class might implement serializable for data conversion, comparable for sorting, and authenticatable for login operations. Each interface represents a different abstract capability. This composition of capabilities through multiple interfaces provides incredible flexibility. We can mix and match capabilities as needed for each class. A shopping cart might be serializable and discountable, but not authenticatable. A product might be serializable, comparable, and reviewable. Each class gets exactly the capabilities it needs. Interfaces enable programming to abstractions rather than implementations. When we write a function that takes a serializable parameter, it works with any class that implements that interface. We've abstracted away the specific class types, focusing only on the capability we need. This principle, called dependency inversion, states that high-level code should depend on abstractions, not on concrete implementations. Instead of a function requiring a MySQL database object specifically, it requires a database connection interface. Instead of requiring a file logger, it requires a logger interface. This makes code more flexible and testable. We can swap implementations without changing the code that uses them. In production, we might use a real database. In testing, we might use a mock database. The code doesn't change because it depends on the abstraction, not the implementation. Let's explore data abstraction, another important aspect. Data abstraction means representing complex data as simple types. Instead of working with raw bytes and memory addresses, we work with integers, strings, and objects. Instead of managing individual database records, we work with collections of objects. Object Relational Mapping, or ORM, systems are excellent examples of data abstraction. A database stores data in tables with rows and columns. An ORM system abstracts this as objects. You work with product objects, user objects, and order objects. Behind the scenes, the ORM translates these into database queries, but you never see that complexity. You call product save, and the ORM generates the appropriate SQL to insert or update a database record. You call user find by email, and the ORM queries the database and constructs a user object from the results. The abstraction lets you think in terms of objects rather than SQL queries. This is powerful because objects are easier to work with than raw SQL in most application code. The abstraction raises the level of thinking. It also makes the code more maintainable. If you change database systems, you might only need to reconfigure the ORM, not rewrite all your data access code. Abstraction also appears in the form of layers in software architecture. A typical application might have several layers: a user interface layer, a business logic layer, and a data access layer. Each layer abstracts the details of the layer below it. The user interface layer works with high-level concepts like display form and handle button click. It doesn't know how business logic is implemented. The business logic layer works with domain concepts like process order and calculate discount. It doesn't know whether data is stored in a SQL database, a NoSQL database, or flat files. The data access layer handles those details. Each layer presents an abstraction to the layer above it. This separation of concerns makes the system easier to understand, test, and modify. You can change how one layer works without affecting others, as long as you maintain the abstraction boundaries. APIs, or application programming interfaces, are abstractions that hide complexity. When you use a web API to get weather data, you make a simple HTTP request and receive JSON data. You don't see the weather station network, the data collection systems, the database queries, or the processing algorithms. All that complexity is abstracted behind a simple interface. This is the power of abstraction at scale. Complex systems can interact through clean, simple interfaces. The complexity exists, but it's hidden behind abstraction layers, making systems manageable and comprehensible. Abstraction requires careful design. You need to choose the right level of abstraction for your problem. Too much abstraction can make code unnecessarily complex and difficult to understand. Not enough abstraction leaves too many details exposed, making the code hard to use and maintain. A common pitfall is premature abstraction. Developers sometimes create elaborate abstraction layers for problems that don't require them. They build interfaces and abstract classes for scenarios where simple concrete classes would suffice. This adds complexity without benefit. The guideline is to create abstractions when you need them, not before. If you're only ever going to have one implementation of something, you probably don't need an interface for it. Create the abstraction when you're adding a second implementation, or when you need the flexibility for testing. Another consideration is abstraction leak. An abstraction leaks when implementation details show through it. If you've abstracted database access behind an interface, but your code needs to know whether it's using SQL or NoSQL to work correctly, the abstraction is leaking. This defeats the purpose of abstraction. Good abstractions hide all implementation details. Code using the abstraction shouldn't be able to tell or need to know how it's implemented internally. If you find yourself checking types or adding special cases based on which implementation you have, your abstraction isn't working well. Let's look at a comprehensive example tying together the abstraction concepts we've discussed. Imagine we're building a notification system that can send messages through various channels: email, SMS, push notifications, and Slack. We create a notification sender interface with a send notification method. This is our abstraction, the capability to send a notification, regardless of how it's sent. We implement this interface in multiple classes: email sender, SMS sender, push notification sender, and Slack sender. Each implements send notification differently, using the appropriate API for its channel. Our application code works with the notification sender interface. When something important happens and users need to be notified, we call send notification on a notification sender object. We don't know or care which specific implementation we have. This abstraction provides enormous flexibility. We can add new notification channels by creating new classes that implement notification sender. We can configure which channels to use without changing application code. We can test the application with a mock sender that doesn't actually send anything. The application is decoupled from notification implementation details. It thinks in terms of the abstract concept of sending notifications, not the specifics of SMTP servers or SMS gateways. This is abstraction managing complexity. We could take this further with additional abstractions. A notification formatter interface might handle formatting messages for different channels. A notification preference system might determine which channels each user prefers. Each abstraction handles one aspect of the problem, and they compose together into a complete system. This compositional approach is fundamental to managing complexity in large systems. Instead of one monolithic notification system that handles everything, we have multiple abstractions that each handle a specific concern. The abstractions connect through clean interfaces. Abstraction also relates to the single responsibility principle. Each class should have one reason to change, one responsibility. By creating appropriate abstractions, we ensure that changes to one aspect of the system don't ripple through unrelated parts. If we change how emails are formatted, we only modify the email formatting code. If we add a new notification channel, we only add a new implementation class. The abstractions create boundaries that contain changes. To summarize, abstraction is the process of hiding complexity and showing only essential details. It involves identifying the relevant characteristics of objects while ignoring irrelevant details. Abstract classes provide partial implementations that child classes complete. Interfaces define pure contracts that unrelated classes can implement. Abstraction enables us to think at higher levels, working with concepts rather than implementation details. It appears in data abstraction, architectural layers, APIs, and design patterns. Good abstraction makes systems easier to understand, use, maintain, and extend. The key is choosing the right level of abstraction for each problem. Create abstractions when they reduce complexity and increase flexibility, but avoid over-abstracting. Ensure abstractions don't leak implementation details. Use abstraction to create clear boundaries between system components. In the next section, we'll explore advanced OOP concepts, including composition versus inheritance, the solid principles, design patterns, and other topics that build on the foundational concepts we've covered. Understanding abstraction well prepares you to appreciate these advanced topics, as they all involve creating and managing appropriate abstractions in different ways. Now that we've covered the fundamental pillars of object-oriented programming, let's explore some advanced concepts that will deepen your understanding and improve your ability to design robust, maintainable systems. These concepts build on what we've already learned and represent best practices that have emerged from decades of object-oriented development experience. Let's start with one of the most important design decisions you'll face: composition versus inheritance. We've already discussed inheritance extensively, but there's an alternative approach to code reuse and modeling relationships: composition. Understanding when to use each is crucial for good object-oriented design. Inheritance models and is a relationship. A lion is an animal. A circle is a shape. These relationships are rigid and hierarchical. Once you define that lion inherits from animal, that relationship is fixed. Inheritance creates tight coupling between parent and child classes. Composition models has a relationship. A car has an engine. A house has rooms. With composition, an object contains other objects as attributes. Instead of inheriting behavior, it delegates to the contained objects. Let's look at a concrete example. Suppose we're modeling vehicles. We might start with an inheritance hierarchy. Vehicle is the parent, with car, motorcycle, and boat as children. This seems natural at first. But then we need to add electric vehicles. Is an electric car its own class? Does it inherit from car? What about a hybrid that's both gasoline and electric? Do we create electric motorcycle as a separate class too? The inheritance hierarchy quickly becomes complicated and rigid. With composition, we approach this differently. A vehicle has an engine. We create different engine types: gasoline engine, electric engine, hybrid engine. A vehicle contains an engine object. To create an electric car, we create a car with an electric engine. A hybrid motorcycle is a motorcycle with a hybrid engine. This is more flexible. We can change a vehicle's engine at runtime if needed. We can add new engine types without modifying the vehicle class. We can combine characteristics more freely. Composition is often more adaptable than inheritance. There's a famous principle in object-oriented design: favor composition over inheritance. This doesn't mean never use inheritance. It means prefer composition when both could work. Inheritance is appropriate for true is a relationships where the child is genuinely a specialized version of the parent. Composition is often better for assembling complex behavior from simpler components. Composition also avoids some problems with inheritance. The fragile base class problem occurs when changes to a parent class break child classes. If many classes inherit from a parent and you modify the parent, all children are affected. With composition, changes to a component only affect classes that use that specific component. Composition provides better encapsulation. A composed object can hide its components completely. External code doesn't know or care what components are inside. With inheritance, the child class is tightly bound to the parent's implementation. Let's consider a practical example: building characters in a role-playing game. We might initially think to create a class hierarchy: character-parent class, with warrior, mage, and rogue as children. Each child has different abilities. But what if players want a multi-class, combining warrior and mage abilities? Do we create a warrior-mage class? What about all other combinations? The inheritance approach becomes unwieldy. With composition, we model this differently. A character has a collection of abilities. We create separate classes for different abilities: sword fighting, spellcasting, stealth, and so on. A warrior character contains sword fighting abilities. A mage contains spellcasting abilities, and a multi-class character contains both. This component-based approach is extremely flexible. Players can mix and match abilities freely. Adding new abilities doesn't require changing existing classes. It's a much more maintainable design than the rigid inheritance hierarchy. Now let's discuss the solid principles, 5 fundamental principles of object-oriented design. These principles, introduced by Robert Martin, provide guidance for creating maintainable, flexible systems. Let's explore each one. The S stands for Single Responsibility Principle. A class should have one and only one reason to change. This means each class should have a single, well-defined responsibility. If a class does too many things, changes to one aspect require modifying the class, potentially breaking other aspects. Consider a user class that handles user data, validates user input, saves users to a database, and sends welcome emails. This class has multiple responsibilities. If we change how emails are sent, we modify the user class. If we change database systems, we modify the user class. If we change validation rules, we modify the user class. Multiple reasons to change means multiple responsibilities. Better design separates these concerns. We have a user class for user data, a user validator for validation, a user repository for database operations, and an email service for sending emails. Each class has one clear responsibility and one reason to change. This makes the code more maintainable and testable. The O stands for open-closed principle. Classes should be open for extension but closed for modification. You should be able to add new functionality without changing existing code. This reduces the risk of breaking working code when adding features. We've already seen this principle in action with polymorphism. When we have a parent class or interface with multiple implementations, we can add new implementations without modifying existing code. Adding a new payment method doesn't require changing the checkout code that processes payments. Strategy patterns, which we discussed earlier, exemplify the open-closed principle. We can add new strategies without modifying code that uses strategies. The code is closed to modification but open to extension through new strategy implementations. The L stands for Liskov substitution principle. Child class objects should be substitutable for parent class objects without breaking the program. If code expects a parent type, it should work correctly with any child type. We touched on this when discussing polymorphism. This principle is violated when a child class changes behavior in ways that break code expecting the parent's behavior. If a parent class method never throws exceptions, but a child's override does, code that doesn't handle exceptions will crash. The child isn't truly substitutable for the parent. Ensuring Liskov substitution means child classes should strengthen guarantees, not weaken them. They can do more than the parent, but they must do at least what the parent promises. Method preconditions can be strengthened in children. Postconditions can be weakened. This principle ensures polymorphism works reliably. When we write code that works with parent types, we can trust that any child type will work correctly. This trust is fundamental to polymorphic design. The I stands for interface segregation principle. Clients shouldn't be forced to depend on interfaces they don't use. Large interfaces with many methods should be split into smaller, more specific interfaces. Classes then implement only the interfaces they actually need. Imagine a worker interface with methods like work, eat lunch, take break, and file taxes. A human worker implements all these methods. But if we have a robot worker, it doesn't eat lunch or take breaks. It shouldn't be forced to implement those methods. Better design creates multiple smaller interfaces, workable with a work method, food consumer with an eat lunch method, rest requirer with a take break method. Human implements all three. Robot implements only workable. Each class implements exactly the interfaces it needs. This principle keeps interfaces focused and prevents classes from having unnecessary dependencies. It's related to the single responsibility principle, but applied to interfaces rather than classes. The D stands for dependency inversion principle. High-level code should depend on abstractions, not concrete implementations. Both high-level and low-level modules should depend on abstractions. This inverts the typical dependency flow, where high-level code depends directly on low-level code. We've seen this principle with interfaces and dependency injection. Instead of a high-level order processor class directly creating a MySQL database object, it depends on a database interface. A MySQL database implementation is injected into it. The high-level code depends on the abstraction, not the concrete database. This inversion makes code more flexible and testable. We can swap database implementations without changing order processor. We can inject a mock database for testing. The high-level logic is decoupled from low-level implementation details. These 5 solid principles work together to create well-designed object-oriented systems. They're not rigid rules, but guidelines that help you make design decisions. When you face a design choice, Considering these principles helps you choose approaches that will be more maintainable and flexible. Let's move on to design patterns. Design patterns are reusable solutions to common problems in software design. They're not finished code you can copy and paste. They're templates that describe how to solve a problem in a way that's been proven effective. The most famous design patterns come from the Gang of Four book, which categorized patterns into creational, structural, and behavioral patterns. Let's explore a few important ones. The singleton pattern ensures a class has only one instance and provides a global access point to it. This is useful for things like configuration managers or database connection pools, where you want exactly one instance shared across the application. A singleton class has a private constructor so external code can't create instances directly. It has a static method that returns the single instance, creating it on first access. Subsequent calls return the same instance. This guarantees only one instance exists. However, singletons are controversial. They introduce global state, which can make testing difficult. They create hidden dependencies. Code using a singleton depends on it, but this dependency isn't visible in constructors or method signatures. Use singletons sparingly and consider whether dependency injection might be a better approach. The factory pattern creates objects without specifying their exact classes. Instead of calling constructors directly, you call a factory method that decides which class to instantiate based on parameters or configuration. This is useful when object creation is complex or when the exact type needed isn't known until runtime. A shape factory might have a createShape method that takes a string parameter. Pass in circle, get a circle object. Pass in rectangle, get a rectangle object. The calling code doesn't need to know about specific shape classes. Factories encapsulate object creation logic, making it easier to change or extend. If you add a new shape type, you modify the factory, not all code that creates shapes. This supports the open-closed principle. The observer pattern defines a one-to-many dependency between objects. When one object changes state, all its dependents are notified automatically. This is fundamental to event-driven programming and user interface systems. Imagine a weather station that collects data. Multiple displays show this data: current conditions, statistics, forecasts. When the weather station gets new data, all displays need to update. The observer pattern handles this elegantly. The weather station is the subject. It maintains a list of observers, the displays. When data changes, the subject calls an update method on each observer. Each display observer implements update to refresh its display with new data. The subject doesn't need to know what observers do. It just notifies them. This pattern decouples the subject from observers. The weather station doesn't depend on specific display types. New displays can be added without modifying the weather station. It's a flexible way to handle notifications and updates. The strategy pattern encapsulates algorithms in classes, making them interchangeable. We discussed this earlier when talking about polymorphism. A class that needs an algorithm accepts a strategy object and calls its methods, without knowing which specific algorithm is being used. This is useful when you have multiple ways to perform an operation and want to choose between them dynamically. Sorting algorithms, compression algorithms, validation strategies, all benefit from the strategy pattern. The decorator pattern adds functionality to objects dynamically without modifying their class. Instead of creating subclasses for every combination of features, you wrap objects in decorator objects that add behavior. Consider a coffee shop system. You have a coffee class. Customers can add milk, sugar, whipped cream, caramel, and other options. Creating a subclass for every combination is impractical. You'd need coffee with milk and sugar, coffee with milk, sugar, and whipped cream, and hundreds more. With the decorator pattern, you wrap the coffee object in decorator objects. A milk decorator wraps coffee and adds milk functionality. A sugar decorator wraps the result and adds sugar. Decorators can be stacked freely, creating any combination without class explosion. Each decorator implements the same interface as the object it decorates. Code that works with coffee works with decorated coffee too. The decoration is transparent to client code. These are just a few design patterns. There are many more, each solving a specific problem. Learning design patterns gives you a vocabulary for discussing design and a toolkit of proven solutions. However, don't force patterns where they don't fit. Use patterns when they genuinely simplify your design, not just to use a pattern. Let's discuss coupling and cohesion, two fundamental concepts for evaluating code quality. Coupling refers to how dependent classes are on each other. Cohesion refers to how focused a class is on a single purpose. Low coupling is desirable. Classes should depend on each other as little as possible. Changes to one class shouldn't require changes to many others. We achieve low coupling through abstraction, interfaces, and dependency inversion. Classes depend on abstractions rather than concrete implementations, reducing coupling. High cohesion is desirable. A class should be focused on one thing and do it well. Methods in the class should be closely related, all contributing to the class's single purpose. High cohesion usually follows from the single responsibility principle. The ideal is low coupling and high cohesion. Each class does one thing well and doesn't depend heavily on other classes' internals. This makes code more maintainable, testable, and flexible. Consider a hypothetical order processor class. If it directly creates database connections, constructs email messages, validates credit cards, and updates inventory, it has low cohesion. It's doing too many unrelated things. It also has high coupling. It depends on specific database, email, payment, and inventory systems. Better design extracts these responsibilities into separate classes that order processor depends on through interfaces. Order processor becomes focused on order processing logic, achieving high cohesion. Its dependencies are through abstractions, achieving low coupling. Another advanced concept is dependency injection, which we've mentioned several times. Dependency injection means providing an object with its dependencies rather than having it create them. There are three main approaches: constructor injection, setter injection, and interface injection. Constructor injection passes dependencies through the constructor. When creating an object, you provide everything it needs. This makes dependencies explicit and ensures the object is fully initialized before use. Setter injection provides dependencies through setter methods after construction. This is useful when dependencies are optional or might change during the object's lifetime. However, it risks having partially initialized objects if setters aren't called. Interface injection defines an interface with a method for injecting the dependency. Objects implement this interface to receive their dependencies. This is less common than the other approaches. Dependency injection frameworks automate this process, managing object creation and dependency wiring. Popular frameworks include Spring for Java, and many languages have similar tools. These frameworks examine constructor parameters or annotations and automatically provide the necessary dependencies. Dependency injection promotes testability. When an object's dependencies are injected, you can inject mock versions for testing. You can test the object in isolation without needing real databases, network services, or other complex dependencies. Let's wrap up this section by discussing some advanced OOP features found in various languages. Mixins allow adding functionality to classes without inheritance. A mixin is a class that provides methods to other classes, but isn't meant to be instantiated itself. Languages like Ruby and Python support mixins, allowing flexible code reuse beyond single inheritance. Traits, similar to mixins, are collections of methods that classes can include. Unlike interfaces, traits can contain implementations. Unlike traditional inheritance, a class can include multiple traits, getting functionality from each. Generic programming allows writing code that works with any type, specified when the code is used. A list class can be generic, working with lists of any type, integers, strings, or custom objects. The implementation is the same regardless of element type. Generics provide type safety without code duplication. Instead of writing int list, string list, and dozens of other specific list types, you write one generic list that works with any type. The compiler ensures type safety. A list of integers can't accidentally contain strings. Reflection allows code to examine and modify its own structure at runtime. You can discover what methods a class has, call methods by name stored in strings, and even modify class definitions dynamically. Reflection is powerful but should be used carefully as it can make code harder to understand and maintain. Aspect-oriented programming addresses cross-cutting concerns, functionality that spans multiple parts of a system, like logging, security, or transaction management. Instead of scattering this code throughout your classes, aspect-oriented programming lets you define it separately and apply it automatically to designated areas. These advanced features extend object-oriented programming in various ways, providing additional tools for solving complex problems. Understanding when and how to use them comes with experience and depends on your specific language and problem domain. To summarize this section, we've explored composition as an alternative to inheritance, often providing more flexibility. We covered the solid principles: single responsibility, open-closed, list-off substitution, interface segregation, and dependency inversion. We examined several design patterns including singleton, factory, observer, strategy, and decorator. We discussed coupling and cohesion as measures of code quality, and dependency injection as a technique for managing dependencies. Finally, we touched on advanced features like mixins, traits, generics, and reflection. These advanced concepts build on the fundamentals to create more sophisticated, maintainable designs. They represent best practices learned from decades of object-oriented development. In the next section, we'll look at how these concepts apply in practice, examining real-world applications, common pitfalls to avoid, and best practices for writing effective object-oriented code. Now that we've covered the theory and principles of object-oriented programming, let's explore how OOP is applied in real-world scenarios. Understanding the concepts is one thing. Knowing how to apply them effectively in practice is another. In this section, we'll examine practical applications, common pitfalls developers encounter, best practices for writing effective OOP code, and how different languages implement these concepts. Let's start by looking at real-world applications, where object-oriented programming truly shines. Web applications are perhaps the most common domain where OOP is extensively used. Modern web frameworks like Django for Python, Ruby on Rails, Spring for Java, and ASP.NET for C# are all built on object-oriented principles. In a typical web application, you have models that represent database tables as classes. A user model might have attributes like username, email, and password, with methods for authentication and profile management. A product model represents items for sale with pricing and inventory methods. An order model ties users and products together with order processing logic. These models aren't just data containers. They encapsulate business logic. The user model knows how to hash passwords securely. The product model knows how to calculate discounts based on current promotions. The order model knows how to validate that items are in stock before completing a purchase. This encapsulation keeps logic organized and maintainable. Controllers in these frameworks are classes that handle HTTP requests. Each controller method corresponds to a different endpoint. A user controller might have methods for registration, login, profile viewing, and profile editing. The controller orchestrates the application flow, coordinating between models, business logic, and views. Views or templates render data for display. In some frameworks, views are also objects that can contain presentation logic. The separation between models, views, and controllers is itself an application of object-oriented design principles, separation of concerns, and single responsibility. Game development is another domain where OOP is essential. Games are naturally object-oriented. Players, enemies, items, levels, and game mechanics are all modeled as objects. Unity, one of the most popular game engines, is heavily object-oriented. Everything in Unity is a game object with various component objects attached. A game character might be composed of multiple components: a renderer for visuals, a collider for physics, a health manager for tracking damage, an AI controller for behavior, and an animator for movements. Each component is a separate class, focused on one aspect of the character. This composition-based approach makes it easy to mix and match functionality. Enemies in a game might all inherit from a common enemy class, but have different behaviors. A zombie enemy might slowly follow the player. A ranged enemy might keep distance and shoot projectiles. A boss enemy might have multiple attack patterns and phases. Polymorphism allows the game to treat all enemies uniformly in some contexts, while each exhibits unique behavior. Mobile applications rely heavily on OOP. iOS development uses Objective-C or Swift, both object-oriented languages. Android development uses Java or Kotlin, also object-oriented. Mobile apps are structured around view controllers or activities, classes that manage different screens of the app. Each screen in your app is typically a separate class. A login screen class handles authentication. A feed screen class displays content. A profile screen class shows user information. These classes coordinate with model classes representing data and service classes, handling network requests, database access, and other background operations. Enterprise software, the complex systems used by businesses, is built with OOP at every level. Enterprise applications deal with immense complexity, thousands of business rules, integration with multiple systems, workflows spanning departments, and massive amounts of data. OOP helps manage this complexity through layered architectures. The presentation layer contains classes for user interfaces. The business logic layer contains classes encoding business rules and processes. The data access layer contains classes managing database operations. The integration layer contains classes communicating with external systems. Each layer depends on abstractions from the layer below, not concrete implementations. This allows each layer to be developed, tested, and modified independently. Teams can work on different layers simultaneously, without constant conflicts. The system remains maintainable despite its size. Banking systems, healthcare systems, logistics systems, all rely on carefully designed object-oriented architectures. A banking system might have classes for accounts, transactions, customers, loans, and hundreds of other concepts. Each class encapsulates the rules and behaviors for its domain concept. Desktop applications like Photoshop, Microsoft Office, and development environments are built with OOP. These applications have complex user interfaces with menus, toolbars, panels, and documents. Each UI element is an object with its own state and behavior. The document you're editing in Word is an object containing paragraph objects, which contain text-run objects with formatting. Each element knows how to display itself, respond to user input, and save itself to disk. This hierarchical object structure mirrors the hierarchical nature of documents. Now let's discuss common pitfalls and anti-patterns in object-oriented programming. Recognizing these mistakes helps you avoid them in your own code. The God object anti-pattern occurs when one class knows too much or does too much. It's called a God object because it acts like it's omnipotent, controlling everything. God objects violate the single responsibility principle spectacularly. They're enormous classes with thousands of lines of code and dozens or hundreds of methods. God objects are problematic because they're hard to understand, hard to test, and hard to modify. Any change risks breaking something else. Multiple developers can't work on them simultaneously because everyone needs to modify the same file. God objects should be refactored into multiple smaller, focused classes. The anemic domain model anti-pattern occurs when domain objects contain only data with no behavior. Classes have getters and setters, but no methods that do anything meaningful. All logic lives in separate service classes that manipulate the anemic objects. This isn't really object-oriented programming. It's procedural programming disguised with classes. The power of OOP comes from encapsulating data with the operations on that data. Anemic models lose this benefit, while there are some architectural styles where this separation is intentional. Typically, you want domain objects with rich behavior. Yo-yo problem refers to inheritance hierarchies so deep that understanding behavior requires bouncing up and down through many class levels. You look at a method in a child class, which calls a parent method, which calls another parent method, which calls back to an overridden method in the child. Following the execution flow becomes dizzyingly complex. Deep inheritance hierarchies should generally be avoided. Favor shallow hierarchies with composition. If you find yourself creating inheritance trees more than 3 or 4 levels deep, reconsider whether inheritance is the right approach. The circle ellipse problem illustrates issues with modeling mathematical relationships in code. Mathematically, a circle is a special case of an ellipse where both radii are equal. So you might make circle inherit from ellipse. But this creates problems. An ellipse can have its radii set independently. A circle shouldn't allow this. Both radii must always be equal. The inheritance relationship that seems natural mathematically doesn't work well in code. This illustrates that object-oriented modeling isn't always a direct translation of real-world or mathematical relationships. You need to consider behavioral compatibility, not just conceptual relationships. The Liskov substitution principle helps identify when inheritance relationships will work correctly. Overusing design patterns is another pitfall. Some developers, upon learning design patterns, try to apply them everywhere. They create factories for simple object creation, singletons for things that don't need to be singletons, and elaborate observer systems for simple notifications. This creates unnecessary complexity. Design patterns should be applied when they solve a problem, not because they're patterns. Start with simple, straightforward code. Introduce patterns when the code's complexity justifies them. Don't prematurely over-engineer. Premature abstraction is related. Some developers create elaborate inheritance hierarchies, interfaces, and abstraction layers before they're needed. They try to predict all future requirements and build flexibility for every possible change. This creates complex systems that are hard to understand and often don't provide flexibility where it's actually needed. Follow the principle of YGNI. You aren't going to need it. Build what you need now, not what you might need someday. When requirements change, refactor. Good design makes refactoring manageable. Trying to predict every possible change up front is both impossible and counterproductive. Let's discuss best practices for writing effective object-oriented code. These practices help you avoid pitfalls and create maintainable systems. Write small, focused classes. Each class should have a clear, single responsibility that you can describe in one sentence. If you struggle to describe what a class does without using words like and or, it probably has multiple responsibilities and should be split. Keep methods short and focused too. A method should do one thing at the appropriate level of abstraction. If a method is dozens of lines long with multiple levels of indentation, it's doing too much. Extract pieces into helper methods with descriptive names. This makes code easier to read and test. Favor immutability when practical. Immutable objects can't be changed after creation. Instead of modifying an object, you create a new one with the desired changes. This eliminates whole categories of bugs related to unexpected modifications. Immutable objects are easier to reason about and safer in concurrent systems. Not everything can or should be immutable, but consider it as a default. Make attributes final or constant when possible. Provide methods that return new objects rather than modifying existing ones. This functional approach within object-oriented code often produces more reliable systems. Use meaningful names. Class names should be nouns describing what the object is. Method names should be verbs describing what the method does. Avoid abbreviations unless they're universally understood. The name should clearly communicate purpose without requiring additional documentation. A class named DMPR is meaningless. Database Migration Progress Reporter is clear. A method named do is useless. Process pending orders is descriptive. Good names are one of the simplest and most effective ways to make code maintainable. Program to interfaces, not implementations. When a method parameter or attribute is a type, use the most general type that provides the functionality you need. If you need a list, use a list interface, not an ArrayList implementation. This maximizes flexibility. Callers can provide any list implementation, and you can change implementations later without affecting callers. This applies to return types too. Return the most general type that makes sense. If a method returns a collection, return the interface type, not a specific implementation. This hides implementation details and gives you flexibility to change them. Write comprehensive tests. Object-oriented design makes code testable by allowing dependencies to be injected and mocked. Take advantage of this. Unit tests test individual classes in isolation. Integration tests test how classes work together. Good test coverage catches bugs early and gives you confidence to refactor. Tests also serve as documentation. They show how classes are meant to be used. When someone wants to understand how to use your user class, They can look at user tests and see examples of creating users, authenticating them, and updating profiles. Document your public interfaces. While code should be self-documenting through good names and clear structure, complex behavior still needs explanation. Document what methods do, what parameters mean, what they return, and what exceptions they throw. Document any non-obvious behavior or edge cases. Don't document the obvious. If a method named getUserEmail returns the user's email, that doesn't need documentation. Document the non-obvious. Does it return null for users without emails, or an empty string, or throw an exception? These are the details developers need to know. Review and refactor regularly. Code quality degrades over time as features are added and requirements change. Regular refactoring keeps code clean. When you add a feature and notice a class is getting too large, refactor it. When you see duplicated code, extract it into a shared method or class. Refactoring is easier with good tests. Tests ensure you don't break functionality while restructuring. Without tests, major refactoring is risky. With comprehensive tests, you can refactor confidently, knowing tests will catch any mistakes. Let's examine how different programming languages implement object-oriented concepts. While the principles are universal, syntax and features vary significantly. Java is a purely object-oriented language. Everything except primitive types is an object. Java has explicit access modifiers, public, private, protected, and package private. It supports single inheritance, but multiple interface implementation. Java requires explicit type declarations and uses static typing with compile time type checking. Java's approach emphasizes explicit design. You declare exactly what's public and what's private. Interface contracts are clear. The compiler catches type errors before runtime. This verbosity can feel cumbersome, but provides safety and clarity. Python is object-oriented, but more flexible. Everything in Python is an object, including functions and classes themselves. Python doesn't enforce encapsulation. There are no true private attributes. By convention, attributes starting with an underscore are considered internal, but they're still accessible. Python uses duck typing. If an object has the method you need, it works, regardless of its actual type. You don't need formal interfaces. You just call methods and handle exceptions if they don't exist. This flexibility makes Python code more concise, but less explicit than Java. C++ supports object-oriented programming, but also allows procedural and generic programming. It has powerful features like multiple inheritance, operator overloading, and templates for generic programming. C++ gives programmers fine control over memory management and performance, but with increased complexity. JavaScript is prototype-based rather than class-based, though modern JavaScript has class syntax. Objects can inherit directly from other objects without classes as intermediaries. JavaScript is dynamically typed and extremely flexible. Properties and methods can be added to objects at runtime. C# combines features from Java and C++. It's statically typed like Java, but supports more modern features like properties, which combine attribute storage with getter and setter logic. C# has excellent tool support and integrates closely with the .NET framework. Ruby emphasizes developer happiness and productivity. It's purely object-oriented. Even primitive values are objects. Ruby supports mixins for sharing behavior across unrelated classes. It's dynamically typed and has flexible syntax that reads almost like natural language. Swift, Apple's modern language, combines object-oriented and protocol-oriented programming. Protocols are like interfaces, but more powerful. Swift emphasizes safety with features like optionals for handling null values explicitly. It supports both classes and structs, with structs being value types that are copied rather than referenced. Each language has its strengths and philosophies. Java and C# emphasize enterprise development with strong typing and explicit design. Python and Ruby prioritize developer productivity and flexibility. C++ prioritizes performance and control. JavaScript enables dynamic web applications. Swift focuses on safety and modern language design. Understanding these differences helps you apply OOP concepts appropriately in each language. What's idiomatic in Python might be awkward in Java, and vice versa. Learn your language's conventions and leverage its strengths. Finally, let's discuss object-oriented programming in different types of projects. Small scripts and utilities might not need elaborate OOP designs. Simple procedural code or basic classes might suffice. Don't over-engineer small programs. Medium-sized applications benefit greatly from OOP. Clear class structures, interfaces, and design patterns keep complexity manageable. This is where OOP truly shines, providing organization without overwhelming overhead. Large enterprise systems require careful architectural planning. Layered architectures, dependency injection frameworks, and rigorous design patterns become essential. These systems need formal designs reviewed by multiple senior developers. The complexity demands the structure OOP provides. Microservices architectures apply OOP within each service while keeping services loosely coupled. Each microservice is a focused application with its own object model. Services communicate through APIs, not by sharing objects. This combines OOP benefits within services with architectural flexibility between services. To summarize, object-oriented programming is used extensively in web applications, games, mobile apps, enterprise software, and desktop applications. Common pitfalls include God objects, anemic domain models, deep inheritance hierarchies, and overusing patterns. Best practices include writing small focused classes, using meaningful names, programming to interfaces, writing tests, and refactoring regularly. Different languages implement OOP differently, from Java's explicit static typing to Python's flexible duck typing. The scale and nature of your project influence how extensively you apply OOP principles. Always match your design to your actual needs, rather than applying patterns dogmatically. In the next section, we'll explore modern trends in object-oriented programming, including how OOP interacts with functional programming, how it's evolving in modern languages, and when alternatives to OOP might be more appropriate. We'll look at where OOP is headed and how it remains relevant in contemporary software development. Object-oriented programming has been the dominant paradigm for decades, but software development continues to evolve. In this section, we'll explore how OOP is changing in modern languages, how it interacts with other programming paradigms, particularly functional programming, and when you might choose alternatives to traditional OOP. We'll also look at current trends and where object-oriented programming is headed in the future. Let's start with the evolution of OOP in modern programming languages. While the core principles remain the same, newer languages are refining how these principles are expressed and adding features that address shortcomings in older object-oriented languages. Modern languages increasingly emphasize immutability and value types. Traditional OOP focused on mutable objects that change state over time. Modern approaches recognize that immutable data structures eliminate whole categories of bugs, especially in concurrent and distributed systems. Languages like Kotlin, Swift, and Rust encourage or require immutability by default. In these languages, you explicitly mark things as mutable when needed rather than marking things as constant. This inverts the traditional approach, making immutability the safe default. Kotlin, which runs on the Java virtual machine, demonstrates modern OOP evolution. It maintains compatibility with Java while adding features that make OOP more pleasant and less error-prone. Null safety is built into the type system. Variables are non-nullable by default. You must explicitly declare when null is allowed. This eliminates the notorious null pointer exceptions that plague Java. Kotlin also provides data classes, which automatically generate common methods like equals, hashcode, and toString. This reduces boilerplate code. Extension functions allow adding methods to existing classes without inheritance, providing flexibility without hierarchies. These features show how modern languages are streamlining OOP. Swift, Apple's language for iOS and macOS development, similarly modernizes OOP. It distinguishes between classes, which are reference types, and structs, which are value types. Structs are copied when assigned or passed, while classes are referenced. This distinction gives developers control over whether objects share state or maintain independent copies. Swift's protocol-oriented programming extends beyond traditional interfaces. Protocols can have default implementations, providing behavior without inheritance. Multiple protocols can be composed, and types can conform to protocols without being related through inheritance. This is composition taken to the language level. Rust takes a radically different approach to object-oriented concepts. It doesn't have traditional classes or inheritance, yet it provides encapsulation, polymorphism through traits, and composition. Rust's ownership system ensures memory safety without garbage collection, solving problems that plague traditional OOP languages. Rust demonstrates that you can have object-oriented benefits without traditional object-oriented mechanisms. Its trait system provides polymorphism, its structs provide encapsulation, and composition replaces inheritance entirely. This shows how OOP principles can be implemented in non-traditional ways. Now let's explore the intersection of object-oriented and functional programming. For years, these paradigms were seen as opposing approaches. Object-oriented programming emphasizes mutable state and objects that change over time. Functional programming emphasizes immutable data and pure functions without side effects. Modern consensus is that these paradigms are complementary, not contradictory. The best code often combines ideas from both. This hybrid approach is sometimes called multi-paradigm programming, and it's becoming the norm in many modern languages. Functional programming concepts increasingly appear in object-oriented languages. Higher-order functions, functions that take other functions as parameters or return functions, are now common. Java 8 introduced Lambda expressions and the Stream API, bringing functional concepts to a traditionally object-oriented language. Instead of writing loops to process collections, you use functional operations like map, filter, and reduce. These operations don't mutate the collection, they return new collections. This functional approach within an object-oriented language produces cleaner, more declarative code. Map transforms each element in a collection using a function. Filter selects elements matching a condition. Reduce combines elements into a single result. These operations can be chained together, creating processing pipelines that are easier to understand and reason about than traditional imperative loops. Consider processing a list of products to find expensive items and get their names. The imperative approach uses loops and conditionals, building up a result list. The functional approach chains filter and map operations. Filter products by price, then map to names. The functional version is more concise and declarative. Immutability from functional programming improves object-oriented code. Instead of methods that modify objects, you have methods that return new objects with desired changes. A setPriority method doesn't change the task's priority. It returns a new task with the updated priority. The original task remains unchanged. This might seem inefficient, creating new objects constantly. But modern languages optimize this with techniques like structural sharing, where unchanged parts of objects are shared between copies. The immutability benefits outweigh any performance costs in most applications. Pure functions, another functional concept, are functions with no side effects. Given the same inputs, they always return the same output. They don't modify global state, don't do I/O, don't depend on external mutable state. Pure functions are easier to test, reason about, and parallelize. In object-oriented code, you can't make everything pure. Objects inherently have state, but you can minimize side effects. Methods that only compute results from parameters and object state without modifying anything are essentially pure. The more of your code that's pure, the easier it is to understand and test. Functional composition, building complex functions from simpler ones, applies to object-oriented design too. Small, focused methods that do one thing can be composed into more complex operations. This is similar to the single responsibility principle, but applied at the method level. The strategy pattern we discussed earlier is essentially functional programming within OOP. Strategies are functions encapsulated in objects. Modern languages often allow passing functions directly, eliminating the need for strategy objects. This simplifies the pattern while keeping its benefits. Some languages fully embrace multi-paradigm programming. Scala, for instance, is both object-oriented and functional. Everything is an object, but functions are first-class values. You can use mutable state or immutable data structures. You can use inheritance or composition. Scala developers mix paradigms freely, choosing appropriate approaches for each problem. F# on the .NET platform is primarily functional but supports object-oriented features. You can define classes and use inheritance when appropriate, but the language encourages functional approaches. This flexibility lets you use OOP for modeling domains while using functional programming for algorithms and transformations. The key insight is that paradigms are tools, not religions. Object-oriented programming excels at modeling complex domains with entities, relationships, and behaviors. Functional programming excels at data transformations and concurrent processing. Using both where each fits produces better code than dogmatically sticking to one paradigm. Let's discuss when not to use object-oriented programming. OOP isn't always the best choice. Some problems are better solved with other approaches. Simple scripts and one-off tasks don't need elaborate class hierarchies. If you're writing a script to rename files or process a CSV, straightforward procedural code is fine. Creating classes would add complexity without benefit. Use the simplest approach that works. Data-intensive transformations often work better with functional approaches. If you're processing large datasets, transforming data through pipelines, functional operations on immutable data can be clearer and more efficient than object-oriented approaches. MapReduce, the paradigm behind big data processing, is fundamentally functional. Highly concurrent systems sometimes struggle with traditional OOP. Mutable shared state is difficult to synchronize correctly. Actor models, where independent actors communicate through messages, avoid shared state entirely. Each actor maintains its own state and processes messages sequentially, eliminating synchronization issues. Languages like Erlang and Elixir use actor models successfully for highly concurrent, fault-tolerant systems. Actors have some object-oriented characteristics, encapsulating state and behavior, but they communicate purely through message passing, not method calls. This is OOP adjacent but fundamentally different. Systems programming, building operating systems, device drivers, and embedded systems, often uses procedural or low-level approaches. Fine control over memory and hardware is more important than abstraction. C remains dominant in this space, and while C can be used in an object-oriented style, it's typically used procedurally. Event-driven and reactive programming represent another paradigm. Instead of objects calling methods on each other, components react to events. RxJava, React, and similar frameworks use reactive approaches. These can coexist with OOP. Components are objects that respond to event streams, but the overall architecture is reactive rather than object-oriented. That said, OOP remains valuable even in these contexts. A script might use a few classes to organize code. Functional transformations operate on objects representing data. Actor systems use objects to encapsulate actor state. OOP often plays a supporting role even when it's not the primary paradigm. Let's look at current trends shaping the future of object-oriented programming. One major trend is the move toward composition over inheritance. Modern design increasingly favors flat structures of composed objects over deep inheritance hierarchies. Component-based architectures in game engines, web frameworks, and UI systems exemplify this trend. Instead of inheritance trees, entities are composed of components. A game character isn't a subclass of movable entity, which is a subclass of entity. Instead, it's an entity with movement, rendering, health, and AI components attached. This approach is more flexible and avoids inheritance problems. Adding new behaviors means adding new components, not creating new subclasses. Combining behaviors means combining components. The entity component system architecture in games demonstrates composition at scale. Another trend is dependency injection becoming standard practice. Frameworks like Spring for Java and equivalents in other languages make DI the default way to structure applications. New developers learn DI from the beginning rather than as an advanced technique. This promotes loose coupling and testability throughout code bases. Microservices architecture represents a trend towards smaller, more focused components. Each microservice is independently deployable, often in its own programming language. Services communicate through APIs, not shared code. This is OOP principles applied at the architectural level. Encapsulation, Clear interfaces, single responsibility, but for entire services rather than classes. Domain-driven design, or DDD, is increasingly influential. DDD focuses on modeling the problem domain accurately in code. Domain experts and developers collaborate to create a shared language reflected in class and method names. The code structure mirrors the business domain, making it easier for non-technical stakeholders to understand. DDD emphasizes rich domain models, where objects contain both data and business logic. This counters the anemic domain model anti-pattern. Objects represent real domain concepts with meaningful behaviors, not just data containers. This makes code more maintainable and aligned with business needs. The rise of cloud computing influences OOP practice. Cloud-native applications need to be stateless, scalable, and resilient. Traditional OOP with long-lived stateful objects doesn't always fit this model. Cloud applications often combine OOP for business logic with stateless architectures for deployment. Serverless computing takes this further. Functions as a service execute individual functions in response to events with no persistent state. Each function invocation starts fresh. This works well with functional programming, but can incorporate OOP. Functions can instantiate objects, perform operations, and return results without maintaining state between invocations. Machine learning and artificial intelligence are influencing how we think about objects and behavior. Instead of explicitly programming behavior, objects might learn behavior from data. A recommendation system object doesn't have hard-coded recommendation logic. It has a trained model that predicts recommendations. This is still object-oriented in structure, but differs in how behavior is defined. Type systems are evolving. Gradual typing, where you can mix typed and untyped code, appears in languages like TypeScript and Python with type hints. You get type safety where you want it without being forced into declaring types everywhere. This combines flexibility with safety. Algebraic data types and pattern matching, features from functional languages, are appearing in object-oriented languages. These provide powerful ways to model data and handle different cases. Swift's enums with associated values, Kotlin's sealed classes, and Java's pattern matching and switch expressions bring these functional features to OOP languages. Looking to the future, object-oriented programming will continue evolving. Pure OOP languages that force everything into classes are declining. Multi-paradigm languages that support OOP alongside functional, procedural, and other approaches are ascendant. Flexibility is valued over ideological purity. We'll likely see continued blending of paradigms. Object-oriented concepts like encapsulation and polymorphism remain valuable, but they'll be used alongside functional concepts like immutability and pure functions, reactive concepts like event streams, and whatever new ideas emerge. Education is shifting too. Computer science courses increasingly teach multiple paradigms. Students learn that OOP is one tool among many, not the only way to program. This produces developers who can choose appropriate approaches for each problem rather than forcing everything into an object-oriented model. New languages will continue refining OOP concepts. We'll see better type systems, better support for composition, better concurrency primitives, and better ways to express domain concepts. The core ideas of encapsulation, abstraction, and polymorphism will persist, but their expression will keep improving. Object-oriented programming isn't dying, but it's maturing. The initial enthusiasm for pure OOP has tempered into pragmatic use of OOP where it fits. This is healthy. Programming paradigms are tools, and mature developers know when to use which tool. The problems OOP solves, modeling complex domains with multiple interacting entities, managing large code bases, and enabling team collaboration, remain relevant. As long as we build complex software systems, we'll need techniques to manage that complexity. OOP provides proven techniques that work at scale. But OOP isn't magic. It doesn't automatically make code good. Poor OOP is as problematic as poor procedural or functional code. Understanding principles, applying best practices, and knowing when to bend or break rules separates good developers from mediocre ones. To summarize, modern languages are refining OOP with features like null safety, data classes, and better type systems. Object-oriented and functional programming are converging in multi-paradigm languages. Immutability, pure functions, and functional operations complement object-oriented designs. OOP isn't always the best choice. Simple scripts, data transformations, and some concurrent systems work better with other approaches. Current trends include favoring composition over inheritance, widespread dependency injection, microservices architectures, domain-driven design, and cloud-native patterns. Type systems are evolving, and features from functional languages are appearing in OOP languages. The future is multi-paradigm flexibility rather than paradigm purity. Object-oriented programming remains relevant and valuable. It's evolving, not dying. Understanding both its strengths and limitations, knowing when to use it and when to combine it with other approaches, is essential for modern software development. In our final section, we'll conclude this comprehensive overview of object-oriented programming, summarizing key points and providing resources for continued learning. We'll tie together everything we've covered and set you on a path for further exploration of OOP and related concepts. We've covered an enormous amount of ground in this comprehensive exploration of object-oriented programming. From the fundamental concepts of classes and objects to advanced design patterns and modern trends, we've examined how OOP helps us build complex, maintainable software systems. Now let's tie everything together, summarize the key points, and provide you with resources and guidance for continuing your OOP journey. Let's recap the core concepts we've explored. Object-oriented programming organizes code around objects, which bundle data and behavior together. This mirrors how we naturally think about the world, making code more intuitive and manageable. OOP emerged in the 1960s with Simula, matured through Smalltalk in the 70s, and became mainstream in the 80s and 90s with C++, Java, and Python. Classes serve as blueprints that define what objects will contain and what they can do. Objects are instances of classes, concrete entities, with their own state. Attributes store an object's data, while methods define its behaviors. This encapsulation of data with the code that operates on it is fundamental to object-oriented thinking. Encapsulation goes beyond just bundling. It's about controlling access and hiding implementation details. We use access modifiers like public, private, and protected to control visibility. Private attributes are protected from direct access, and we provide public methods with validation and business logic to interact with them safely. This protects object integrity and allows internal changes without breaking external code. Inheritance enables code reuse by creating new classes based on existing ones. Child classes inherit attributes and methods from parents while adding their own unique features or overriding inherited behaviors. Inheritance models is a relationships and creates hierarchies that reflect domain structure. However, deep inheritance trees can become problematic, and composition is often a better alternative. Polymorphism allows objects of different types to be treated uniformly through a common interface. Runtime polymorphism through method overriding lets us write code against parent types that works with any child type. Compile-time polymorphism through method overloading provides multiple versions of methods with different parameters. Polymorphism enables flexible, extensible designs that are open for extension but closed for modification. Abstraction focuses on essential characteristics while hiding irrelevant details. Abstract classes and interfaces define contracts that concrete classes must fulfill. They let us program to abstractions rather than implementations, reducing coupling and increasing flexibility. Abstraction manages complexity by working at appropriate levels of detail, from low-level data structures to high-level architectural layers. These four pillars, encapsulation, inheritance, polymorphism, and abstraction, form the foundation of object-oriented programming. Understanding how they work individually and together is essential for effective OOP. We explored advanced concepts that build on this foundation. Composition versus inheritance taught us that as a relationships often work better than is a relationships. Favor flexible composition over rigid inheritance hierarchies. The solid principles provide guidance for good design, single responsibility, open-closed, Liskov substitution, interface segregation, and dependency inversion. Design patterns offer reusable solutions to common problems. Patterns like singleton, factory, observer, strategy, and decorator represent accumulated wisdom from decades of object-oriented development. They're not code to copy, but approaches to understand and apply when appropriate. Don't force patterns where they don't fit. Use them when they genuinely improve your design. Coupling and cohesion measure code quality. Low coupling means classes depend on each other minimally, making changes less risky. High cohesion means classes are focused on single, clear purposes. Strive for loosely coupled, highly cohesive designs. Dependency injection helps achieve this by inverting dependencies and allowing flexible configuration. We examined how OOP is used in practice across web applications, games, mobile apps, enterprise systems, and desktop software. We identified common pitfalls like God objects, anemic domain models, and over-engineering. Best practices include writing small focused classes, using meaningful names, programming to interfaces, writing comprehensive tests, and refactoring regularly. Different programming languages implement OOP differently. Java emphasizes explicit design with static typing. Python provides flexibility with duck typing. C++ offers power and control. JavaScript uses prototypes. C# combines features from multiple languages. Swift introduces modern safety features. Understanding your language's approach helps you write idiomatic code. Modern OOP is evolving, incorporating ideas from functional programming. Immutability, pure functions, and functional operations complement object-oriented designs. Multi-paradigm languages let you choose appropriate approaches for each problem. OOP remains valuable, but is one tool among many, not the only way to program. Current trends favor composition over inheritance, widespread dependency injection, microservices architectures, domain-driven design, and cloud-native patterns. The future is multi-paradigm flexibility, not paradigm purity. New languages refine OOP concepts with better type systems, null safety, and features borrowed from functional languages. So where do you go from here? How do you deepen your understanding and improve your object-oriented programming skills? Let me provide some guidance and resources. First, practice is essential. Reading about OOP gives you knowledge, but only writing code develops skill. Start small projects that apply OOP concepts. Build a library management system, a task tracker, a simple game, anything with multiple interacting entities. Design the classes, implement them, refactor as you learn. Don't aim for perfect design initially. Make mistakes, recognize them, and refactor. Learning happens through iteration. Your first attempt won't be great, and that's fine. Each project teaches you something. Over time, good design becomes intuitive. Contribute to open source projects. Reading professional code teaches you how experienced developers structure systems. See how large code bases are organized, how classes interact, how abstractions are used. Contributing forces you to understand existing designs and work within established patterns. This experience is invaluable. Study design patterns deeply. The original gang of 4-book, Design Patterns, Elements of Reusable Object-Oriented Software, is still relevant decades after publication. It's dense but worth the effort. Headfirst Design Patterns provides a more accessible introduction with visual explanations and examples. For solid principles and clean code practices, read Robert Martin's books. Clean code covers writing readable, maintainable code at every level from naming to functions to classes. The Clean Coder addresses professional practices and attitudes. Agile Software Development, Principles, Patterns, and Practices explores object-oriented design comprehensively. Martin Fowler's books are essential for serious developers. Refactoring teaches you how to improve existing code safely through small, incremental changes. Patterns of Enterprise Application Architecture covers patterns for building large systems. His website, martinfowler.com, contains numerous articles on software design topics. Domain-Driven Design by Eric Evans revolutionized how we think about modeling business domains in code. It's challenging but transforms how you approach design. If you work on business applications, DDD concepts will make you significantly more effective. For modern perspectives on OOP and its intersection with functional programming, explore languages like Kotlin, Swift, and Scala. Learning how these languages blend paradigms expands your thinking beyond any single approach. Even if you don't use these languages professionally, understanding their approaches improves your code in any language. Online resources are abundant. Websites like Refactoring Guru explain design patterns with clear diagrams and multiple language examples. YouTube channels offer tutorials on OOP concepts. Coding challenge sites like LeetCode, HackerRank, and Code Wars provide practice problems that can be solved using object-oriented approaches. However, be selective with online resources. Quality varies widely. Prioritize content from recognized experts, established publishers, and reputable platforms. Random blog posts and videos may contain misconceptions or outdated practices. Cross-reference information and favor sources that explain why, not just what. Join programming communities. Participate in discussions on Stack Overflow, Reddit's programming subreddits, or specialized forums for your language. Ask questions, answer others' questions, and engage in discussions about design decisions. Teaching others reinforces your understanding and exposes you to different perspectives. Find a mentor if possible. An experienced developer can review your code, suggest improvements, and guide your learning. Many developers are willing to mentor. Look for mentorship programs. Ask at local user groups, or reach out to developers you admire. Mentorship accelerates learning dramatically. Conversely, mentor others when you're able. Explaining concepts to beginners clarifies your own understanding. You'll encounter questions you can't answer, motivating you to learn deeper. Teaching is one of the best ways to master a subject. Take courses, either online or in person. University courses provide structured, comprehensive education. Online platforms like Coursera, edX, and Udemy offer courses from beginner to advanced levels. Look for courses that include projects, not just lectures. Building projects cements learning. Read code regularly. Browse GitHub repositories for well-known projects. Study how they're structured, what patterns they use, how they handle common problems. Reading diverse code bases exposes you to different approaches and broadens your toolkit. Experiment with different languages. Each language community has its own culture and idioms. Learning Java after Python, or vice versa, shows you different ways to apply OOP concepts. Languages shape how you think. Polyglot programmers are more flexible and creative. Practice code reviews, both giving and receiving. Reviewing others' code develops your critical eye and exposes you to different coding styles. Receiving reviews teaches you what experienced developers consider important. Constructive code review is one of the most effective professional development tools. Attend conferences and meetups when possible. Hearing experts discuss current topics, networking with other developers, and participating in workshops provides learning opportunities and professional connections. Conference talks are often recorded and available online if you can't attend in person. Stay current with your language's evolution. Languages add new features regularly. Java now has lambda expressions and streams. Python added type hints. C# continuously adds syntax improvements. Learning new features keeps your skills sharp and often introduces better ways to express object-oriented concepts. Remember that learning is continuous. Even expert developers constantly learn. Technologies change, best practices evolve, and new patterns emerge. Cultivate curiosity and a growth mindset. Every project is an opportunity to learn something new. Balance theory and practice. Too much theory without practice leaves you unable to apply concepts effectively. Too much practice without theory leads to repeating the same mistakes. Read books and articles to understand principles, then apply them in projects. Reflect on what works and what doesn't. Don't be dogmatic. OOP is valuable, but not always the answer. Know when to use it and when alternatives are better. Flexibility and pragmatism beat ideological purity. The goal is building effective software, not perfectly pure object-oriented code. Learn from mistakes. Every bug you fix, every refactoring you do, teaches you something. Don't get discouraged by imperfect code. Professional developers write imperfect code all the time. What matters is recognizing issues and improving continuously. Set concrete goals. Don't just say, I want to get better at OOP. Say, I will build a project using the strategy pattern this month, or I will refactor my existing code to follow solid principles. Specific goals provide direction and measurable progress. Document your learning. Keep notes on concepts that confused you and how you came to understand them. Write blog posts explaining topics you've learned. This solidifies your understanding and creates a reference for yourself and others. Finally, be patient with yourself. Object-oriented programming has depth. You won't master it in weeks or even months. Years of experience develop intuition for good design. Every experienced developer was once a beginner who struggled with the same concepts you're learning now. The journey from understanding basic classes to designing complex systems takes time. Enjoy the process. Celebrate small victories. Each concept you grasp, each project you complete, each refactoring that improves your code represents progress. Object-oriented programming is a powerful paradigm that has shaped software development for decades and will continue to be relevant for years to come. The concepts we've covered in this video provide a comprehensive foundation. You understand what OOP is, why it matters, how its core mechanisms work, and how to apply them effectively. But this is just the beginning. The real learning happens as you write code, make mistakes, refactor, collaborate with others, and continuously improve. Take the concepts from this video, apply them in your projects, explore the resources we've discussed, and commit to ongoing learning. Whether you're building web applications, mobile apps, games, or enterprise systems, object-oriented programming gives you tools to manage complexity, organize code, and build maintainable systems. Use these tools wisely, combine them with ideas from other paradigms, and always focus on solving real problems effectively. Thank you for investing your time in learning about object-oriented programming. I hope this comprehensive overview has given you a solid foundation and inspired you to explore further. Keep learning, keep coding, and keep improving. The world needs skilled developers who understand how to build robust, maintainable software systems. You're on your way to becoming one of them. Good luck on your programming journey, and may your objects always be well encapsulated, your inheritance hierarchy shallow, your polymorphism elegant, and your abstractions appropriate. Happy coding!